So let's start with plasma sources. When we talk about plasma sources are mostly associated with atomic absorption spectroscopy and comparatively less associated with atomic emission spectroscopy. So under plasma sources, there are two types of plasma sources: inductively coupled plasma source and direct current plasma source. In inductively coupled plasma source, the energy is provided to the gas to form plasma in the form of induced field. Those Tesla coils are used. Very interesting to see. Then there is other type. It is called as direct current plasma source, in which the energy is provided initially to generate plasma in the form of current, specifically direct current. So there will be electrodes that will be involving in direct coupled plasma sources, and in case of inductively coupled plasma source there will be induction coil. So by looking at the name itself, you can guess, you can understand the two important differences between these two plasma sources. The term plasma, when you say plasma in biological system, the plasma is something different in terms of physics, in terms of pharmaceutical analysis, analytical. Plasma is a state of matter, as it is gas, liquid, solid. This is also a state of sample, state of matter. It is called as homogeneous mixture of gaseous atoms. Although it is said as gaseous atoms, the plasma is something not exactly gaseous. In that gaseous atoms, you have ions and you have significant quantities of electrons, and all of them are present at very high temperatures. One such plasma source, you know it very well, you see it, you feel it, you experience it every day. That plasma source is right up there in the sky. We call it as sun. Two types of plasma atomic emission sources are frequently used. These are the two types. We discussed the names thereof. And let's start with inductively coupled plasma. This is the actual image of inductively coupled plasma source. You can see the induction coil which is present over here, and you can see there is something glass tubings here. There is one middle tube, there is one glass tube around it, and at the end opening of the outer glass tube, you can see something like flame sort of coming out, but characteristic of that is not matching with the flame. It is white, absolutely white, and it is jetting upward. I hope you can see that jet stream like a structure coming out of the tip. These two are different representations of the construction of the same inductively coupled plasma source. We will see both of them. Both of them are easy to understand. Let's start with this middle one, that blue color jacket. This is the coolant tube. That means you need to cool something. So that is done with tangential airflow, which comes around here. Inside it is a green color tube. It is here written as argon plasma gas inlet. It simply means we are going to pass argon inside it, which will get later on converted to plasma. So it is not that we are passing plasma, we are injecting plasma from here. It is the argon that is entering from here. Later on, it will be converted to plasma. And at the centermost glass tube is sample aerosol inlet. That means sample, if it is a liquid, first we need to convert that to aerosol, and that aerosol will enter over here. The liquid sample itself will not enter here. Okay, the solid sample will not enter here. I hope you understood the bottom half of the assembly. The green tube, when it reaches towards the upper end, it is now called as plasma tube. You must have guessed it. The plasma will start forming here because of these two coils over here. Actually, the cross section shows that it is different to coils, but if you see here, it is the same coil. If you take cross section from here, you will get these two as can say circles over here. So you have RF induction coil. So radio frequency induction coil, or simply you may also label it as induction coil. In bracket, induction frequency is in the range of radio frequency. So that induction field is changed with that high speed. Now that high speed induces the you can say the plasma energy. It starts the argon that is coming from here and the sample that is coming from here. It gets turbulent over here. They increase their energy. The energy is acquired due to induction frequency, a changing induction coil, and it comes out as a jet. Okay, that argon is converted to plasma. The sample gets emitted, and that plasma has very high temperature. Immediate in proximity with a radio frequency induction coil, the temperature is as high as 10,000 Kelvin. You can imagine how hot that area is. Then at the middle, you have 8,000 Kelvin, and near the tip of the flame, that means somewhere here, the temperature is 6,000 Kelvin. Now, depending on the area through which you are passing your electromagnetic radiation will be selected carefully depending on the temperature. At different temperatures, different analytes can be measured. Now, there is another representation of the same thing. ये जो यहाँ पे present किया है, it is another representation of the that. Let's start with bottom again. At the center, you have sample aerosol or vapor of the analyte dispersed in argon. Okay, so it is aerosol. Now this is coming here, and there is small opening if you can see. So this is the sample getting injected. Now this is tangential argon plasma support flow. So argon is flowing tangentially, and then it is getting mixed here with the sample. Now, two different arrangement in these two is here are saying argon plasma gas inlet and tangential air inflow. They're different. Okay, you may get confused with this, but actually it is the same thing. I will tell you how. See, here the sample aerosol and argon plasma inlet, they have mentioned it properly separately, and here they're saying that the aerosol is already mixed with argon. So it is the same thing, and this is tangential argon flow, and this is also tangential argon flow. So this part is matching. It is like we are taking cross section from here and looking over here. Okay, so this is the induction coil. You can see 2I presenting the current that is flowing through it, producing the induction. The current is with radio frequency. So the induced field H is also changing with radio frequency. You can see the blue color intense high temperature region, which is corresponding to this region over here. And this is the plasma. If you will see this light pink colored ring, in that lightly pink colored ring, ionization of flowing argon is achieved by spark. A spark is induced in the presence of that induction coil. That spark initiates the ionization of the argon. This ionized argon interacts with strong magnetic field, which is induced by the induction coil. Try to imagine that argon is now ionized, and these ions are interacting with that strong magnetic field. Now, when that interaction occurs, that ionized argon will be forced to move within the vicinity of the induction coil at very high speed. So the argon ions will start to form a vortex-like structure. They will start moving in a circular path with very high speed, and it will be very difficult for them to escape from there, because ion which is in motion will have its own magnetic field, and it will be difficult for that ion to escape that magnetic field. Okay, so I hope you can imagine, because of spark, argon has got ionized. Those ionized ions are moving with very high energy in the magnetic field. Now, can imagine that there will be lots of collisions of ions and unionized argon. Then with your sample, everything is there is lot of motion there. So very high temperature is obtained as a result of the very high resistance experienced by circulating organ. Where this high resistance is coming from? See, more and more of the argon and the sample, the aerosol is entering in the region. When they are entering the region, they are not ionized. They themselves are not ionized. So they will oppose the flow of that circulating argon ions. You can imagine that. See, suppose say 5 or 6 people are running around in a ground. They're doing circles of the ground, and suddenly some huge crowd of 100 odd people starts entering the ground. So they are bound to bump into each other. So this happens in the same manner. So the area which is highlighted in that pink circle, all these commotions are occurring there, and as a result of the collisions, of the ignition, and because of the induced force, everything, the temperature goes very high. This is called as ohmic heating. Ohm, it is related to resistance. So there is resistance also, and overall temperature in this region goes very high. Now consider this pink region now. This region is made up of quartz. So the top of the quartz tube will experience very high temperatures because of all the motions and heating we have seen in previous step. And it should be insulated and cooled. Otherwise, it is quartz, it will can crack, it can may break. Now, this is accompanied by tangentially passing the argon flow. It is used for two purposes now. It is cooling the quartz. Also, it is used in the ohmic heating in this region. So the tangential argon has two functions here now. It should also be indicated that argon consumption is relatively high, because you require argon as aerosol also, and you require argon for cooling off also. And argon is little difficult to obtain gas. So because of this large requirement of argon, ICP, that is inductively coupled plasma source, become little bit costly. These are the different temperature regions you can see. A region which is highlighted in blue color over here, okay, that is these regions, okay, not immediately in that vortex or the region where uh, ionized argon and everything is getting heated at very high temperature, not that region. This is the region where elements are generally viewed around 6000 to 7000 Kelvin temperature. This distance, if you will observe, it is typically between, say, how much it must be, 12 centimeters to 25 centimeters from the tip of the coil. So from this is above the coil. Now moving forward, see, this argon is quite a unique inert gas. The argon gas itself has very few emission lines. So what is the advantage of argon having very few emission lines? It will not interfere with the spectra given by the elements in this region. Or even if it is interfering, we can easily identify which lines are given by argon, and we can ignore it as a background noise. Ionization in plasma may be thought to be problem at very high temperatures. If the temperature reaches very high, the ionization itself may be a problem, because if your sample gets ionized extensively, the ion of your analyte, suppose you are analyzing potassium, you are analyzing sodium, you are analyzing calcium, the lines given by atomic calcium line, when I say lines, I mean to say line spectra given by calcium is different than that of calcium ion. So you will be not able to analyze your sample accurately. So ionization may be a problem. It is okay to obtain temperature using those ions, but if that ionization goes out of hand, it causes problem. The advantage of using argon is argon compared to all other atoms, all other elements, is considered to be as easily ionizable. So the logic is similar. If you add argon, if something has to ionize, it itself will ionize. Like this is the same logic. You add antioxidants in your pharmaceutical formulation. Why you add antioxidants? These are the compounds which themselves get oxidized. They have very high oxidation potential, so they in a way protect others. So argon here is protecting other elements from getting ionized. So this is how actually the plasma sources they appear. Coming to the next plasma source, direct current plasma. Now, direct current plasma, there is actual photo of it on your left hand side. This is the, you can say, actual photograph, and on your right hand side is the block diagram of it. Now, there is one shadow, if you can see over here. Let me zoom into it. I hope you will be able to see if I zoom in. Okay, I hope you can see a shadow in there. The tip of that probe,
Hello,
tip
sir.
of that probe is visible. That is a capillary from which sample is introduced in this plasma. Now let us understand the, can say, the working and construction of it. See, there are two electrodes. Okay, these electrodes are made up of graphite. Okay, now these graphite electrodes are hollow. So you can imagine there are two electrodes. That blue color part is electrode. Okay, this blue colored part is electrode, and it is a cylinder, although thick, but it is a cylinder, thick walled cylinder. From center of it, argon is introduced. Okay, now there is another, a tungsten electrode. Now this is not graphite electrode, this is tungsten electrode, and it is attached to a very, I can say, the solid support of tungsten. Now when electrode, this electrode is lowered, okay, the spark is ignited, and the argon that is coming out of the electrode gets converted due to that high potential, high electricity into a plasma. Let's see the working of it. Okay, now first focus on the electrode part. So overall you can see that there are three electrodes. This is one electrode, and these two are another two electrodes. So there are overall three electrodes. And if you will see this yellow color plasma, it is shaped like inverted Y. It is shaped like inverted Y. Now, the upper electrode is made up of tungsten, and it is a cathode. The lower two, both are anodes, and this is cathode. These two are anodes. And you can easily say that although it is having some distance above that anode, it is in a way resting on them. Okay, there is very small gap between them, but it is in a way resting on them. Now what happens is that upper electrode, the tungsten block, is slightly lowered while the argon is passing through all these three electrodes. Okay, it is slightly lowered. Argon is passing through all these three electrodes. Momentarily, cathode and anode comes in contact with each other. When it is lowered, it comes in middle, and electricity start flowing through the electrodes. Okay, and because of that electricity, the argon inside it gets ionized, and the moment this happens, the tungsten electrode is lifted. It is now in no more contact with the graphite anode electrodes. Okay, it is lifted from there. So when it is not in directly contact and argon is ionized, it is heated, the argon coming from the center gets heated, ionized, and its act as the current carrying element between two electrodes. It carries the current between anode and cathode. Meanwhile, as the current is flowing, these graphite electrodes, because they have high resistance, they also start heating. So it becomes a cycle that argon, when it is coming, it will first get heated because of the electricity flowing through. It will get ionized, and you get a plasma formed between the cathodes and anodes. And the plasma will be of inverted Y shape. When sample is introduced into this plasma, this is the region where sample will get converted into atomic state, and this region is called as excitation region. Plasma comparison. So what are advantages of direct current plasma? It uses comparatively less argon. We do not require argon for cooling. The simpler instrumental requirements and less spectral line interference, because obviously argon is less in number, so you will have less interference spectra. But if you will observe that there are graphite electrodes which are getting heated, so obviously wear and tear of those graphite electrodes will be observed. So disadvantages: anodes are frequently changed because they get oxidized. Relatively, this is less sensitive. What is advantages of inductively coupled plasma? It is convenient to work with. It is free from frequent consumables, and it is comparatively more sensitive. Now, advantages of plasma sources overall. There is nothing getting burned, sort of. There is no LPG or any methane gas or something that is getting ignited. So no oxide formation as a result of two factors, including they involve very high temperature and inert environment. Inside of the plasma there is no oxygen, so oxidation of the cell is avoided. So we have seen before also oxides of the analyte give different spectral lines. Minimum chemical interferences. Because of high temperature, the sample is very fast is converted to atoms, and parallel chemical reactions are low in number. Minimum spectral interferences, except for higher possibility of spectral line interference due to exceedingly large number of emission lines because of high temperature. See, if we heat a gas, if we heat a gas, it, as the temperature goes on increasing, instead of giving the line spectra, it tends to give a band spectra. What is band spectra? There are a lot of excitation emissions. Next, uniform temperature, which results in precise illumination. Unlike flame, there is no flickering. So if you select a region of the plasma, it is more probable that it will maintain its temperature. Okay, yes, provided you maintain the argon flow to a constant rate. No self-absorption is observed, which extends the linear dynamic range of higher concentration. So if you go on increasing the temperature in flame, the if you go on increasing the temperature in the flame, the other atoms which are not that excited because of comparatively lower temperature, comparatively lower energy, will start absorbing the emitted light by other excited atom. But in plasma sources, because that uniform high temperature region, most of the atoms are at higher energy levels. So if they are at higher energy level, they will not self-absorb. There is no electron in that lower level to absorb the energy. So no self-absorption is observed. No need for a separate lamp for each element. So in conventional flame, many times different mixture and different arrangement of the flame uh, is required, so that the atoms that are produced will be able to absorb the electromagnetic radiation produced by the source. Okay, so different lamps will be required for every element. Here it is not possible. Here it is not needed. Easily adaptable to multi-channel analysis. That means you can analyze multiple analytes in single go.